Good evening, everyone, and welcome to today's class. In the previous class, we were dealing with series and parallel combination of capacitors, and we had seen what we had seen. We had seen what happens when capacitors are connected in series. Yes or no? We had seen some points of capacitors connected in series. Charge is same. Voltage is inversely proportional to capacitance. If equal capacitors are connected in series, then you will have equivalent capacitance coming as C by N. Do we remember this, everyone? Yes or no?
Sir.
Important points. We remember this. Now,
Yes, sir.
I just need you to remember, you add one or two important points here also. We had seen that the potential is inversely proportional to C. You can also write one more point here. The energy stored in each capacitor in series is also inversely proportional to C. I've seen questions on this and I missed it in the previous class. So just add this note into the points that we have written, that energy is also inversely proportional to your capacitance, whereas the charge coming on each capacitor, as you have seen, is same. So charge remaining same, voltage of each capacitor, voltage drop across each capacitor is inversely proportional to C, whereas the energy stored in the capacitor is also inversely proportional to C. Have you noted this down? Important point, you just need to add it here. I hope you had some space there. There you could have added this. Yes or no? No, yes. Return this.
Yes, sir.
One more point that you could add here, and I'm going to add it here. Whenever capacitors are connected in series, and you can see here that the equivalent capacitance becomes C by N. So actually the equivalent capacitance is less than the original capacitance. That is what you need to remember. Whenever capacitors are connected in series, whenever capacitors are connected in series, the equivalent capacitance will always be less than any of the capacitors. So if you have a combination of, and this is how a question can be asked. If you have, let us say, capacitor whose capacitance is 2, 3, 4, 5, and so on, and when you connect them in series, what will be the equivalent capacitance? Remember, the equivalent capacitance will be less than the lowest one. So it will always be lesser than all of the capacitors or any individual capacitors. The equivalent capacitance is always less than the individual capacitance. Do we understand this?
Yes, sir.
Okay, so that was your series combination, and I think we have done a couple of questions, more than a couple of questions, and everyone has understood the concept of series capacitance.
Sir,
Yes, beta.
last one, repeat.
Last, sorry,
Last one, Pura. Sir, can you please explain this one?
which point, beta?
C equivalent. C equivalent. C.
C equivalent is less than C. C. Now look at this example. Three capacitors of capacitance 2, 3, and 6, they are connected in series, and we have found out the equivalent capacitance, and see, the equivalent capacitance is coming as 1. It is less than all of the three. In fact, it is less than the smallest of them also. That is what I wanted to say. Whenever you have capacitors connected in series, if you find out the equivalent capacitance will always come less than any of these capacitors. We understand this? Do we understand this? We understand this? One more example here. Two capacitors, 3 microfarad and 6 microfarad are connected in series. When I calculated their effective capacitance, it was coming as 2 microfarad, which is less than 3, which is less than 6. So whenever you connect capacitor in series, the equivalent capacitance that you will get will always be less than all of the capacitors. In fact, it is less than the smallest one. Do we understand this? Or you
Sir.
need more explanation? Do we understand this?
Yes, sir.
Here also, see, we had 10 equal capacitors of capacitance, 5 microfarad. When we found out the effective capacitance, it was coming only half microfarad. When you connect capacitor in series, capacitance is always less than the individual capacitors. Is it clear to everyone now? Yes or no? No or yes?
Yes, sir.
Okay, so that is the only point that I wanted to make. Can you move on to the next combination, my dear friends? Next combination. Next one. Are we ready? Everyone has noted this down? Shall I move ahead, beta? Boys and girls? Okay, I'll give you 2 minutes to note it down. Let me know once you are done. And we move ahead with the next combination, and the next combination is known as the parallel combination. Now, my dear friends, what is going to happen in this parallel combination? You can see in the series combination, charge that was flowing or that charge that was coming on the capacitors was same. Here, what is going to happen? You are going to connect them like this. And I always take the examples of 3 capacitors. I don't know. If the capacitors are connected like this, then we say that they are connected in parallel. This capacitor is C1, this capacitor is C2, and this capacitor is C3. Now what will happen here? All of these plates are connected to positive terminal, so all of these plates will get positively charged and these plates will get negatively charged. Do we understand this, bacha, everyone? The
Yes, sir.
charge will be different. So this will have Q1 charge, this will have Q2 charge, and this will have Q3 charge. I have just named them differently. The first capacitor I will call the pink one, the second capacitor I will call the green one, and the third capacitor I will call the blue one. Everyone understands this till here? Okay, now we have written some formulae for this one. Here also we can write this formulae. So if the total charge which is flowing is Q, the first thing you have to understand is potential drop. Let me not write it as V. The potential difference or potential drop is same across each capacitor and charges are different. Do we understand this, everyone? In this case, potential drop across each capacitor is V. Across this one, it is V. Across this one, it is V. And across this one, also, it is V. Do we understand this?
Sir.
Yes or no? No, yes. So, potential drop, all these things, V, V, V. Potential drop is same, the yellow thing, but the charges are different. As you can see, on this capacitor, we have Q1. On this capacitor, we have Q2. And on this capacitor, we have Q3. Now, what I can do, my dear friends, I can write the value of Q1, Q2, and Q3 also. So I will just write them. If anyone can help me in writing the value of Q1, Q2, and Q3, I would be very glad. How can I write the value of Q1, bacha? Can anyone tell me how can I write the value of Q1? No one? Okay, so Q1 can be written as C1 multiplied by V. C1 is the capacitance, V is the voltage drop. Similarly, I can write Q2 as C2 multiplied by V. Can anyone tell me how can I write the value of Q3? Can anyone tell me how can I write the value of Q3, beta? No one? Okay. So Q3,
C3 V, sir.
C3 into V. That is correct. Um, C3 into V. Now, I can also write one more thing. This total charge Q, this, oops, wrong color. As you can see, this total charge Q will be equal to Q1 plus Q2 plus Q3. In the case of a series capacitor, V total voltage was equal to V1 plus V2 plus V3. Here total charge is equal to Q1 plus Q2 plus Q3. Do we understand this?
Yes, sir.
Now this total charge can be written as C equivalent multiplied by V. What I mean by this C equivalent, I can replace these three capacitors and I can just put one capacitor in place of this. The potential drop would be V and the charge flowing would be Q. This will be the positive plate. This would be the negative plate. Can anyone tell me what will be the value of this equivalent capacitor? What will be the value of this equivalent capacitor? What will be the value of this equivalent capacitor? And in this case, the value of this equivalent capacitor will be C1 plus C2
Sir,
plus C3. Do we understand this?
sir,
Yes, beta?
sir. Once go back, sir.
Okay. Yes. You have not noted it down? So I can replace these three capacitors and put one capacitor. That capacitor is known as equivalent capacitor or effective capacitor or whatever you want to call it. And the value of this C equivalent, as I have already told you just now, what is the value of this C equivalent, beta? C1 plus C2 plus C3. Do we understand this, beta?
Yes, sir.
Have you noted it down, everyone?
Yes, sir.
Okay, well done. So this value of equivalent capacitor is C1, C2, C1 plus C2 plus C3. If there are three capacitors, it will be like this. If there are more, you can just keep on adding more. Now, if n equal capacitors are connected in parallel, if n equal capacitors are connected in parallel, then can anyone tell me what will be the value of C equivalent? If each capacitor has a capacitance equal to C, what will be the equivalent capacitance, bacha? N equal capacitors are connected in parallel. Each capacitor is C. What will be the equivalent capacitance, bacha? It will be equal to N times C. Do we understand this? Do we understand this?
Yes, sir.
And the charge coming on each capacitor will be total charge Q divided by N. Yes or no? So charge will also be equal in this case. Do we understand this better?
Yes, sir.
Now if we write the same point about this, in case of series capacitance, the charge on each capacitor, the charge or Q on each capacitor will be coming directly proportional to C. The capacitor which has more charge, no, the capacitor which has more capacitance will take more charge. The potential V across each capacitor is same because they are connected in parallel. The energy in each capacitor will be proportional to C. Now that if we compare it, if we compare these three things with the parallel connection, my dear friends, you will find out that in parallel connection and in series connection, and I take you back to that series thing, you can see that the potential is proportional to 1 by C, energy is proportional to 1 by C, and charges are same. Do we understand this? That was series. In series, charge was same, potential was inversely proportional to C, and energy was also inversely proportional to C. But as soon as I get into the parallel combination, you can see potential is same, charge is proportional to C, and energy is proportional to C. Do we understand this?
Yes, sir.
Can you remember this? One last thing that you have to remember, in this case, the equivalent resistance will be greater than any individual. So remember, when you want to increase the capacitance, you connect capacitors in parallel. Capacitance will increase. If you want to decrease the capacitance, connect them in series. When you connect them in series, capacitance goes down. When you connect them in parallel, capacitance goes up. Do we understand this? I'll give you 2 minutes to note this down. If you have any doubts, please ask. Please let me know once you are done. Then we come to this question, beta. And I hope you can give me the answer for this straightforward question. The condensers of capacity C1 and C2 are connected in parallel. What is the equivalent capacitance? Yes, bacha. What is the answer for this one, beta? Waiting for your answers. No one knows the answer? It's a straightforward, simple question, beta. Okay.
Option A, sir.
Okay, that is correct. Option A. They are connected in series. The equivalent capacitance of any capacitor connected in series is, you just add them. Here there are two capacitors, C1 and C2. So the answer is C1 plus C2. I hope everyone understands this. Yes or no? Boys?
Yes.
Yes, sir.
Okay. Then comes this one, my dear friends. Question number 2 coming for you. Three capacitance of capacity 10, 5 and 5 are connected in parallel. What is the total capacity? Total capacitance. Yes, my dear friends. What will be the total capacitance, Bacha? No answers? See, sir. Viram gives me an answer. See, sir. Anyone else?
Yes,
What is
sir.
Option C, sir.
option C, sir? That is correct, sir. C1 plus C2 plus C3 is what we have to do, sir. 10 plus 5 plus 5. And the answer is 20. Everyone understand this? Yes or no? No, yes.
Yes, sir.
Comes the next one, sir. And I hope you can give me the answer for this one as well, sir. This is question number 3, sir. Two capacitors connected in parallel having capacity C1 and C2 are given Q charge, which is distributed among them. What is the ratio of the charge on C1 and C2? In what ratio will the charge be distributed, my dear friends? Yes, my dear friends. What will be the ratio of charges, my dear friends? In what ratio will the charge be distributed? They are connected in parallel. Bacha.
Option A.
Option A and option A is correct. Remember, in parallel combination, the charge coming on each capacitor is directly proportional to C. I had already given you that note. Yes or no? No, yes.
Yes, sir.
So if you just remember simple things, you should be able to solve difficult question. Everyone understands this? Can you move forward to the next question?
Yes, sir.
Next question, question number 4, coming for you right away. This one. Three identical capacitors are combined differently for the same voltage to each combination. The one that stores the greatest energy is. Okay, we will do this question afterwards. Let me first give you another question. Then we will come back to this one. First, let us solve some other questions. And then we will come back to this one. Okay, this one we'll do first. This one we will do first because now it will test both our understanding of series and parallel. I'll give you 2 minutes to solve this. Two capacitors. So I'll make this question as question number 4. Two capacitors of equal capacity, so the capacitance is equal, are connected in parallel and then they are connected in series. The ratio of capacities, you have to find out the ratio of capacities in the two cases. I'll give you 2 minutes to solve this. What about the others? Are we getting any answer? I'm getting one answer, option D, which I think is correct. You also got the option D. Let us check. So now I have two capacitors. Let me call the capacitance as C and C. So when they are connected in parallel, my dear friends, when they are connected in parallel, the capacitance becomes C plus C, that is 2C. When they are connected in series, they are equal capacitors connected in series, then the capacitance becomes C by N. So it becomes C by 2. Then you have to find the ratio of parallel combination to series combination. You divide 2C by C by 2. So you get your final answer, and your final answer is definitely 4 by 1 or 4:1, and that is the correct option. And the correct option is C. 4:1. Do we understand this?
Yes, sir.
Everyone understands this? Okay, now let me give you more questions on this. So let us move on to the next question. Let me see if I have ready-made question here somewhere that I can give you. No, it is not there. So I will make a question on my own. So this is the next question that we are going to do. Please note it down. So you have a 3 microfarad capacitor and a 6 microfarad capacitor connected like this across a battery of 2 volts. So I've connected two capacitors like this across the battery 2 volts. You have to find Q, V, and U of each capacitor. Do you understand the meaning of Q, V, and U? What is Q? Q is the charge on each capacitor, V is the potential drop across the each capacitor, and U is the energy stored in the capacitor. I'll give you 2 minutes to do this. Once you are done, please let me know. So how are we supposed to do this? You can do this in many ways. Let me just show you all the ways in which I can do this. One thing is not asked here. One thing is not asked here is the equivalent capacitance. I can also write the value of equivalent capacitance, 3 plus 6. The equivalent capacitance will be 9 microfarad. So that is the first thing that could be asked. Now, if someone asks you to find out the charge on this green capacitor, the simple formula is, remember, the voltage is same. So the voltage is 2 volt. Voltage is 2 volt. Capacitance is 6 microfarad. So you can write Q is equal to CV 6 multiplied by 2. So the answer will be 12 microcoulomb. 12 microcoulomb will be the charge coming on the 6 microfarad capacitor. Do we understand this? Yes or no? Can I now have some voice from your side? Okay, no one is saying anything. I hope everyone understands this. To find out the charge on this capacitor, Q is equal to C into V. C is 3, V is 2. So this will be 6 microfarad. 6 microcoulomb, sorry. Now, if you talk about the potential difference across each capacitor, it is same, and that is equal to 2 volt. So everyone knows the answer for this. Now let me calculate the third thing, which is the energy stored in each capacitor. How will I find the energy stored in each capacitor? So energy stored in the 3 microfarad capacitor, I can use any formula, half CV square, Q square by 2C. Here, since voltage is same, my dear friends, can see voltage is same, so I will use the formula of voltage, and I will use half CV square, half into capacitance of this 3 microfarad is 3 into V square is 4. So I will get the answer as 6. Remember, the answer will come in microjoule. If I had to find out the energy in the 6 microfarad capacitor, my dear friends, again I would do half C into V square. Half into C is 6 into V square is 4. In this case, I will get 12 microjoules. Now there is also two more questions that can be asked. What is the total charge which is flown? What is the total charge? Sometimes they ask you what is the total charge. Now, if you ask your total charge, you know how to find out the total charge. Charge on this is 12, charge on this is 6. So what is the total charge? You just need to add these two charges and you will get the total charge, my dear friends, 18 microcoulomb, which is the same answer, Abhinam, that you are getting, because this is nothing but equal to C equivalent multiplied by V. C equivalent is 9. 9 multiplied by 2. You will again get the answer in that way also. If now they ask you what is the total energy stored in both the capacitors, what you got to do? Nothing much. You just need to add these two energies together. The energy stored in the 3 microfarad capacitor is 6 microjoules. The energy stored in the 6 microfarad capacitor is 12 microjoules. You can add them, and coincidentally both the answers are coming same numerically. The total energy is 18 microjoules. Do we understand this, everyone? Can I get a response from you, beta?
Yes, sir.
How many of you were able to solve the problem? Were you able to do this on your own?
Yes, sir.
Great. If you could do it on your own, that is great. Can I now give you one problem to see whether you can do it all by yourself? Yes or no? No or yes?
Yes, sir.
Okay, then here comes one problem, and I'll ask you everything in that problem. And I hope you are going to give me all the answers very, very correctly. So, this is a question that I'm going to frame for you. You again have a combination of two capacitors connected across a battery. The voltage of this battery is 10 volt. This is 2 microfarad. This is 4 microfarad. You have to tell me everything. Number 1, C equivalent. Number 2, Q, V, and energy of each capacitor. Number 3, Q total and U total, the total energy stored. And I'll give you 2 minutes to do this. I hope you can do this and give me the answer fast. I'll wait. Your time starts now, my dear friends. So the answers for all the cases are here. The charges and the energy stored in all and the work done by the battery. Everyone understands this, what we have done?
Yes, sir.
No, no, yes. Well, that brings us to an end of this session where we were discussing the questions based on the parallel combination of capacitors. In the previous class, we had done the series combination of capacitors. In this class, we have tried to cover the parallel combination of the capacitors. So we now know how to find out the charge, potential, energies in all the cases. Now, this work done by the battery, which is total charge multiplied by V, that could also be found in the previous cases. I thought that we can discuss it today in today's class. So we have discussed this. In the next class, what we will see is we will be seeing different types of combination. These are the very simple combination where all the capacitors were either in series or all the capacitors were in parallel. In next class, we will try to see other combinations also where there will be a mix. Some capacitor would be in series, some capacitor would be in parallel, and we try to solve questions based on this. So that will be coming up tomorrow. I hope everyone has understood today's class. We will continue our session in the next class. Take care and God bless all of you. Bye bye.
Bye, sir.
Bye beta. Everyone understood this?
Yes, sir.
Okay, good. Take care.
Bye, sir. Take care, sir.